Hello and welcome to the Watts Water CEU approved presentation, Solutions to Help Control Legionella. This presentation will walk you through current products on the market used to minimize the risk of Legionella. The pros and cons of each solution will be explored. The content of this program is sponsored by Watts and was first published in Architectural Record magazine in 2017 as a continuing education course titled Solutions to Help Control Legionella. After this presentation, you should be able to identify and recognize the conditions that contribute to the development and growth of Legionella in buildings, investigate the importance and makeup of a water management program as identified in ASHRAE 188, assess the solutions available to address Legionella in water systems, including those that rely on heat, chemicals, and other means, and describe the pros and cons of different water quality solutions that can be effective at reducing Legionella outbreaks. We will explore some of the solutions currently available to help control outbreaks in building water systems for the potentially deadly Legionnaire's disease caused by the Legionella bacteria. Here is the agenda broken down into 7 basic parts. We will start with a broad overview of Legionella and some basic control measures. We will also address the CMS mandate in ASHRAE 188. Both indicate that most hospitals have a water management program and team in place that outlines their plan for Legionella control. Then we will look at the 4 main solutions that involve treating water to reduce the presence of Legionella. We will finish with a quick look at some less common but still available solutions before wrapping up with conclusions. Let's begin by ensuring we are all on the same page about what Legionella is, how its control is typically addressed, and the current regulations. Outbreaks of Legionella bacteria can cause Legionnaire's disease, also known as LD, in any setting, but is a particular concern in healthcare facilities and hotels. The presence of the bacteria can be widespread since it can grow in any part of a water system in a building, such as tanks, piping, fixtures, or water features. In order to infect a person, the Legionella bacteria need to be part of water droplets that become airborne in a manner of aerosol generation. If the infected moisture reaches a person's nose or mouth and is inhaled and settles in the lungs, then it can sicken the person with LD. Since transmission of the bacteria to humans requires it to become airborne, it can occur from things like shower heads, cooling towers, hot tubs, HVAC units, and decorative fountains, to name a few. However, the Legionella bacteria can form and grow before it ever gets to those places, which is why LD outbreaks are generally linked to water in large or complex water systems, including those found in healthcare facilities and hospitality settings. When considering the impact of Legionella, the Center for Disease Control, or CDC, has determined that LD is primarily a health risk for persons who are at least 50 years old, smokers, and those with underlying medical conditions, such as chronic lung disease or immunosuppression. Nonetheless, the disease can, in reality, affect anyone. According to the Mayo Clinic and some other sources, many people exposed to Legionella bacteria don't develop symptoms, but those who do may experience cough, fever, chills, shortness of breath, muscle aches, headaches, and diarrhea. LD is actually a form of pneumonia. Some people who develop LD may think they only have pneumonia and never link it back to Legionella. In severe cases, it has caused death. Treatment typically requires antibiotics, hospitalization, or other care. The CDC has been tracking the number of people who have been diagnosed with LD and have recorded between 8,000 to 18,000 cases annually since the year 2000. While the number of cases is disconcerting, even more so is the trend of growth in the number of outbreaks and infections. The CDC reports that in the U.S., from the year 2000 to 2009, the number of infections increased by a dramatic 217%. Between the years 2000 to 2014, the increase is an even more staggering 400%. It is unclear whether the cases of LD have actually increased this much, or just that we are more knowledgeable about LD and now test for it more regularly. Clearly, this is a serious health concern, and one that comes with a significant price tag. The CDC tells us that the number of direct healthcare dollars it costs in the U.S. to treat a single case of Legionnaire's disease is $34,000. However, this is a very conservative number, and the real costs could be drastically higher. Due to the seriousness of the disease and its linkage to water systems in buildings, ASHRAE has been at the forefront of investigating an effective means of controlling the conditions that will reduce LD outbreaks. Following some initial work in the early 2000s, they published an updated ANSI ASHRAE Standard 188 in 2015 titled Legionellosis: Risk Management for Building Water Systems. This document has become the accepted standard for a comprehensive water management program for buildings where Legionella Control is sought. Specifically, it has been recognized by the CDC, the Department of Health and Human Services, and the Centers for Medicare and Medicaid Services, CMS, as the basis for programs that they administer. In fact, federal funding for many healthcare facilities, particularly those that receive Medicare or Medicaid for payment, must show compliance with an ASHRAE 188 water management program or risk losing reimbursements. A full water management program under ASHRAE 188 is based on a 7-step process that includes assembling a full program team, the survey and documentation of water systems, analysis of water systems, determination of control measures, monitoring, confirmation, and documentation. In order to be effective, the water management program needs to be ongoing and continuous, not just a one-time exercise. As such, it can be integrated into other building operations, policies, and procedures, but it must be able to stand on its own as a complete plan. The entire process requires confirmation and appropriate documentation that the water management program is being carried out and all activity is recorded and documented. The ASHRAE 188 standard is proving to be an effective resource for building operations teams that need real guidance on reducing the risk of LD outbreaks. As a standard, however, it is focused on the process of creating, implementing, and carrying out a full water management program. It does not provide specific solutions for addressing water systems or offer any design components. Design professionals such as engineers, architects, and infection control are required to provide expertise on identifying and analyzing all aspects of the water systems. They need to recommend specific control measure solutions appropriate to the particular building and water system at hand. For full effectiveness, those same design professionals should be involved with ongoing aspects of the water management program. Part of the plan requires ongoing monitoring and water testing for Legionella bacteria and the means to address how it may or may not be transported within a water system. If monitoring reveals a concern, then corrective action must be taken promptly to eliminate it from the system. That means a series of corrective measures must be in place ahead of time to solve the problem immediately. It also means that the normal day-to-day operation needs to allow for ongoing preventative treatments to occur as part of standard operating procedures. That is where attention to all of the plumbing components and choices about their application comes into play, often requiring specialized knowledge of things like expansion and storage water tanks, water treatment systems, mixing valves, drains, backflow valves, and more. In light of everything discussed so far, the specific means to treat water on an ongoing basis, as well as in the case of corrective measure, for a discovered presence of Legionella, deserves some special attention. Toward that end, we will review in the following sections 4 primary types of water treatment solutions, also mentioning some others, which can be considered in a water system design and as part of a full water management program. We will start with heating of water. Facilities that provide hot water throughout the building can consider this solution as part of their overall water management program. It can be very effective because Legionella bacteria are very sensitive to heat. The normal temperature range for Legionella bacteria to grow is between 68 and 122 degrees Fahrenheit. At temperatures below 68 degrees Fahrenheit, it becomes dormant, and at elevated temperatures, it will die. Part of the concern is that the ideal growth range is between 95 and 115 degrees Fahrenheit, which is the typical operating temperature of many hot water systems. Hence, a water management program that seeks to use heat as a treatment solution needs to have the capability to do so, but without the fear of scalding and compromising the safety of people in the building. The premise of a heat solution is that Legionella die within 5 to 6 hours in water heated above 131 degrees Fahrenheit, and more rapidly at higher temperatures. Once the potential sources of water contamination are identified, for example, storage tanks or other components, then the temperatures need to be aligned to assure bacteria does not grow. The most straightforward approach here is for the daily water temperature in a system to be kept above 131 degrees Fahrenheit to kill any bacteria. ASHRAE 188 recommends 140 degrees Fahrenheit as the baseline temperature to kill the bacteria within 30 minutes. In the case of a discovered contamination of the water, the temperature can be raised briefly to around 160 degrees Fahrenheit for a high-temperature flush of the system. This will rapidly kill all of the bacteria in the heated water system and eliminate the threat of a pending outbreak. One of the design considerations of a heating solution is the layout of the piping. If water is being circulated throughout the system and heated at a central source, then there needs to be some certainty that all of the water is making it to the heat. Remote portions of the piping, sometimes referred to as dead legs, may create pockets of water that does not fully circulate. That means any water that sits there for some time is not treated. In those cases, either the dead legs need to be eliminated from the design, or a point-of-use heat solution needs to be incorporated as a supplement to the central heating. Dead legs also reduce the effectiveness of other solutions, such as chlorine and other chemicals. The pros of using heat to control Legionella include that this can be very effective, and it is recommended by ASHRAE 188 as a way to kill bacteria in a matter of minutes to purge a system. The cons include the need to address dead legs, to provide safety against scalding, and the potential of wasting water during a full system flush. Fortunately, all of these cons can be addressed and overcome. While heating water daily to 140 degrees Fahrenheit, or during an incident up into the rapid kill range, is one of the most effective and reliable control measures for dealing with Legionella, it is not necessarily the best temperature for heated water to be used by people. On average, any water above 106 degrees Fahrenheit will cause scalding and pain in humans, while water that is 140 degrees Fahrenheit can cause third-degree burns in a matter of seconds. This is why plumbing codes limit the maximum temperature exiting a fixture at 120 degrees, with the expectation that people can readily control the mix of cold and hot water at the faucet to meet their needs. The solution to this competing set of interests is found in the use of tempering valves or mixing valves that blend hot water that has been generated and stored at temperatures high enough to kill bacteria with cold water in a controlled manner. This ensures constant, safe outlet temperatures while minimizing the occurrences of both scalding and Legionella. When looking at mixing valve options, there are two fundamental types. A point-of-source, or POS system, locates valves at or near the water heating source and typically has a higher capacity for controlled temperature water. A point-of-use, or POU system, uses multiple smaller mixing valves at or near plumbing fixtures such as shower heads, lavatories, whirlpools, and emergency fixtures. Both types are common and have a range of standards issued by the American Society of Sanitary Engineers relevant to particular usage. Beyond purely mechanical mixing valves, computerized digital mixing systems are also available that are considered a smarter and safer way to deliver mixed water throughout a healthcare facility. In this type of system, intelligent control modules and electronically actuated valves are used to allow faster and more accurate response to constant changes in the mixed water delivery demands, often anticipating system changes before they occur. Further, digital water mixing and recirculation solutions can be integrated into a building automation system, allowing facility managers complete control of and visibility into their domestic hot water delivery. As a point-of-source system, certain digital mixing and recirculation stations can provide precise control of hot water delivery within 2 degrees of the set point, surpassing industry standards for mechanical systems. Digital mixing eliminates temperature creep within the system, thus eliminating the need for balancing valves. This means the temperature can more precisely be controlled to mitigate Legionella growth in the heated water. In particular, a sanitation or disinfectant mode can be triggered to briefly raise the temperature above 158 degrees Fahrenheit to induce a rapid kill and purge of all Legionella bacteria. At the same time, the digital mixing system can control temperatures leading to faucets, showers, etc., to reduce the risk of scalding in the mixed water. If combined with separate point-of-use protection, it allows for continuous elevated circulation temperatures to prevent Legionella, per ASHRAE and CDC guidelines. Concurrently, a digital system can control the circulation pump to prevent stagnant conditions or maximize flow rates. Finally, since most large facilities use some type of building automation system, a digital mixing system can be linked to the larger system to communicate and control temperature, pressure, flow, and energy consumption as part of an overall operations and maintenance plan. It also makes documentation and verification more straightforward in a water management program, as called for in ASHRAE 188 and by CMS. From a specification standpoint, most of these systems are easy to install since they typically come pre-piped, pre-wired, and tested, allowing them to carry a warranty from the manufacturer for up to 5 years. The second solution we will look at is the addition of chlorine to water. We will look both at injecting a common dosage on a continual basis and look at adding excessive quantities for breakouts, known as hyper-chlorination. The solution of adding chlorine to water is common to control not just Legionella, but also other bacteria. It is well known for portions of water systems where hot water is not normally used, such as pools, decorative fountains, drinking fountains, etc. But since it is typically a point-of-source solution, it will treat and kill bacteria in all water regardless of temperature. Chlorination of drinking water is routine for municipal water supplies intent on addressing a wide range of bacteria. But at the facility level, there may be a need to alter the chlorine level to assure healthy water quality. This requires a process of on-site chlorination, plus the associated equipment, chemicals, and personnel to go along with it. If chlorine is being added to the water, it is very important to control and monitor the amount being used, particularly if the water is already being received from a municipality with chlorine in it. Too much can be harmful to people, while too little may not disinfect the water, causing potential bacteria outbreaks. To assist in the control and monitoring, there are systems available that inject chlorine at controlled rates for regular daily use. These systems require human oversight, but can otherwise be fairly automated based on water flow. In the case of an outbreak, or if any other concern does arise, then hyperchlorination has been employed as a short-term, high-level corrective measure. This raises the amount of chlorine in the water to between 10 and 15 milligrams per liter, which is much higher than the typical recommended levels of 0.5 to 2 milligrams per liter for daily use. At these higher concentrations, bathing in the water or drinking it is not recommended as it may cause skin irritation or rashes. Note that some water supplies use a variation on chlorine, known as monochloramine, that can cause some poor after effects on the taste and smell of the water after hyperchlorination. Hence, lower levels of added chlorine are called for in this case. Either way, after this hyperchlorination shock to the system, the water needs to be flushed out and replaced with fresh water. There can be some effects on the plumbing system from chlorination, too. Any level over 5 milligrams per liter turns the water acidic, which makes it corrosive to pipes, joints, fittings, and fixtures. If chemical flushing is used with hyperchlorination, then the effects could be more pronounced, since chemical flushing can expose metal surfaces, making them more susceptible to chlorine damage. In addition, chlorine is an excellent electrical conductor, which is significant in plumbing systems that have mixed metals in them, especially common in older buildings. Chlorine passing over these various metals can create an electrical charge that produces galvanic corrosion of the piping and releases metals into the water supply. The result of these chemical interactions are that piping can begin to wear and leak at joints and connections. That can cause significant damage not only to the water system, but to the building as well. The only solution is to replace the water piping, typically embedded in walls, floors, and ceilings, which is clearly a large expense. The pros of chlorination include the relative ease of implementation and a general applicability to both hot and cold water systems. The cons, however, can be numerous. High concentrations can cause unpleasant odors and taste, as well as human health reactions, such as rashes and skin irritations. Further, high concentrations have not proven to be consistently effective at killing Legionella. Separate from human concerns, it can also be harmful to plumbing systems. Corrosion and pinhole leaks have been known to develop over time. And if the chlorine is being added on a regular basis, then such a system will require floor space to store bulk chlorine. All of this reveals hyperchlorination to be one of the most unreliable and one of the most expensive solutions for water treatment. The third, but perhaps lesser-known solution, is to replace the use of chlorine with ions from sacrificial copper and silver that are exposed to the water supply. The use of a carefully engineered copper-silver ionization system is particularly well suited for buildings where the intent is to avoid or reduce the amount of chlorine being used in potable water. Like chlorine treatments, it can be used in either hot or cold portions of the water system, but unlike chlorine, it has almost none of the negative side effects. The process of copper ionization was developed by NASA many years ago as a way to purify drinking water for astronauts in the Apollo space program. It is based on employing positively charged ions from copper and silver plates. These positive ions form an electrostatic bond with negative sites on the cell walls of bacteria. The interaction breaks down the biofilm of the bacteria cells and kills them in the process. Depending on the conditions of the water and the bacteria, the amount of time it takes for the biofilm to be penetrated can vary, but this system has come to be regarded as one of the most effective treatment systems besides heat treatment. Incorporating a system that creates an EPA-approved level of 1.3 parts per million of copper ions and 0.1 parts per million of silver ions has the benefit of providing a consistent, continuous treatment that can be monitored and maintained readily. Typically, the ionization process requires a low-voltage current to free the copper and silver ions into the flow of water, but it is not a particularly significant amount of energy used. The ions become sacrificial in that they are neutralized after the purification process. Therefore, the metal plates that produce the ions need occasional replacement. The pros of a copper-silver ionization solution include a safer treatment of water versus chemical additions such as chlorine. It has also been proven to effectively control Legionella and other pathogens in cold and hot water systems. Eradication of 100% to below 30% Legionella bacteria positivity is achievable, which is considered safe with no LD outbreak. Further, there is prolonged effect up to 3 months after interruption, and it is the only method validated by the 4 steps of the standardized evaluation criteria. Overall, it is a federal EPA-approved system that requires very little square footage to install and operate. The cons include the higher cost to purchase and maintain the system, on the order of $40,000 to $250,000. Compromised efficacy is possible by elevated pH, above 8.5, and low concentration. Because of the nature of the process, the system is required to be registered as a biocide by the EPA. Similarly, personnel who handle the system may need to be licensed in the state where it is located. There is also the possibility that some local jurisdictions may not recognize it as an approved system. The final common solution that we will address here is the use of ultraviolet light exposed to the water in a controlled manner to kill bacteria and other pathogens. In water systems where eliminating the use of chemicals is preferred, this option is to disinfect the water supply with ultraviolet or UV light. An electrical lamp specifically designed to generate UVC radiation is used because of its germicidal properties for disinfection. The lamp is designed to emit nearly monochromatic UVC radiation in the optimum range for absorption by nucleic acids in the cells of microorganisms. The low-pressure lamp, commonly in the shape of a small fluorescent tube, is mounted in a waterproof housing and inserted directly into the stream of supply water, making it an inline system. As the water passes by the lamp, the UV light disrupts the genetic DNA material of any microorganisms, including bacteria, in the water. Sometimes referred to as UV sterilization, this is a simple and rapid physical process that causes molecular rearrangement of the genetic material within microorganisms. This quickly inactivates the microorganisms by destroying their ability to multiply, grow, and ultimately infect people. UV light can be used to control bacteria as part of an overall commercial water treatment system or in residential settings too. Here, the UV component provides pre-disinfection after a water softener and post-disinfection as the final step before water distribution. A centralized UV disinfection system can be highly effective at providing protection against microbiological contamination in water. It can be added as an integral component of a full commercial water treatment system. In this case, UV disinfection has been used as a last step in the water treatment system just before dispensing. UV can also be used as pre-disinfection for reverse osmosis systems to protect the membranes from microbial contamination. The effectiveness of the disinfection depends on the UV dose level delivered, keeping in mind that different organisms require different UV dose levels to be inactivated. These systems are attractive not only because they can be very effective at reducing Legionella bacteria, but also because they are fairly simple to use and operate. The dose produced can easily be set to suit the target organisms by adjusting the UV system's flow rate. Connected to a power source, they produce the UV light that is projected into the incoming water without the need for any chemicals to be handled or added to the water. For large systems, they are commonly completely enclosed for safety to prevent any accidental UV exposure to people. They also typically have sensors indicating their use and performance levels, and can be specified to operate efficiently by only turning on when there is actual water flow in the supply line. They do require monitoring to be sure they are performing properly in a continuous state, but only need minimal maintenance. The pros of a UV light treatment solution are centered on the fact that no chemicals are involved. This means there are no chemicals to store or add, nothing to affect taste, and nothing that reacts with any other impurities in the water. The lack of chemicals also removes the potential for any harm being done to piping and equipment caused by chemical treatments. The cons can include the amount of energy needed to generate the light on a continuous basis, although some units are available that shut off if water is not flowing. The light apparatus needs to be kept clean so the light remains effective, and the water needs to be clear, not turbid. It should be remembered that this is a single-pass treatment at the lamp. There is no residual treatment further on in the system. If warranted, other treatment, such as heat, could be incorporated elsewhere in the system. In addition to the 4 common systems discussed thus far, there are some other strategies that can be incorporated. These may be appropriate for portions of systems or for some specific reasons. There are some alternatives to chlorine, but with a variety of results and effectiveness in regards to Legionella. We have already discussed that monochloramines are used by some municipal water sources because they are seen as a safer alternative to straight chlorine. Monochloramines also have a much lower tendency to convert organic materials into chlorocarbons, such as chloroform and carbon tetrachloride, which can cause their own health risks and detrimental effects on the plumbing. Nonetheless, they still carry some notable concerns, not the least of which is that monochloramines are listed as a carcinogen and a mutagen. Hence, they are typically used in very low concentrations, offering a very stable additive which does not dissipate as quickly as straight chlorine does. So while this chemical may already be present in municipal water and can penetrate a wide range of biofilms and microorganisms, it does bring with it the risk of some harm to people or plumbing if mixed improperly, or if it infiltrates at too high a level. Chlorine dioxide is a neutral chlorine with a chemical structure and behavior that is very different from basic chlorine. It has very high water solubility and remains dissolved as a gas in the water, even at low temperatures. It is sometimes used in smaller secondary distribution lines that have no galvanized piping that could be affected by it. Chlorine dioxide has the advantage of being an EPA-approved biocide that performs better than chlorine when the water pH level is above 7. It also works well in all temperatures of water, and bacteria do not seem to grow resistant to it. As for chlorine dioxide's disadvantages, a licensed individual with a specific license is needed to operate this system, since the material is considered toxic and can become volatile if not stored correctly. Its effect on Legionella is slow, requiring a prolonged exposure to show any reduction. Reactions with organic material in the water or scale on the piping can cause the chlorine dioxide to convert into its byproducts, chlorite and chlorate, which may pose health risks. In general, while both of these chlorine alternatives provide some advantage over straight chlorine, they also bring some other issues that need to be carefully assessed before they are used as part of a full water management program. Water filtration is a common approach to remove contaminants from water. It is appropriate to use regardless of the water source to help prevent contamination of the building water system from incoming water. Filtration is a good supplement to help assure overall water quality, but it will not by itself address the control of Legionella. It can, however, be effective at helping other systems work properly. That is because one of the biggest benefits of water filtration is the removal of sediments and minerals from the water. When those are not filtered, they can build up in the piping and equipment in the form of scale, which can restrict water flow or interfere with the proper operation of other equipment. Sediment and the shadows of sediment in the water can also block other treatments such as UV and copper-silver ionization from penetrating the harmful bacteria. Further, filtration can help with reducing overall bacteria growth, in part because the reduction of scale where it can harbor, and in part from filtering some of it directly out of the water. Scale is essentially food for bacteria. So if sediment and scale can be reduced by filtration, the harmful bacteria have less food to feed upon and grow. As an example of the interaction between filtration and other water treatment system components, a study performed in the mid-1990s at the VA Medical Center in Pittsburgh, Pennsylvania, tested the effects of UV radiation at the point of use on showers in the facility. The UV treatment appeared to work well at first, but then became less effective. They discovered that the incoming hard water was depositing scale on the UV lamp and reducing the amount of UV light that was passing into the water. Once the lamp and housing were cleaned and filters installed to address the hard water, the problem went away and the UV system became a very effective means of controlling Legionella at the facility. Here are some of the pros and cons of using a water filtration system as part of an overall solution. The main takeaway is that while filtration doesn't directly reduce the risk of Legionella growth, it does make all other solutions much more effective. It should be clear that there are many choices available for treating water for Legionella and other concerns. However, not all of them are equally effective nor equally appropriate for different building conditions. No single solution is the answer for all buildings looking to reduce the growth of Legionella in their water systems. In the majority of situations, the most effective solution will include multiple solutions, including at both point of source and point of use. The water management team should carefully consider pros and cons of each solution while determining the best options for their building. As part of the water management program, these solutions should be monitored on a regular basis and other solutions should be reviewed. In all cases, a multi-barrier plan for the mitigation of Legionella is most likely the most effective and appropriate. It is appropriate to review and assess the specific needs of a building facility and to compare them with the available choices to determine what solution is best for that facility. Consultation and input with design professionals and with system suppliers will likely produce the best results. Overall, the goal is to create an effective, ongoing system that helps prevent outbreaks of Legionella, a system that is straightforward to monitor, maintain, and document. Watts Water Technologies, dedicated to improving the comfort, safety, and quality of life for people around the world. Through our industry-leading brands and our expertise in a wide range of water technologies, all of Watts' brands come together to serve your needs.